Alright guys, what I want to do is I want to go over the impulse momentum theorem and shed a little more light into it. Impulse momentum theorem, this is the last thing we covered, and I think you read about it a little bit online. Basically what it states is that if you have an object that experiences impulse, a force over time, we define that as J, that is equal to the change in momentum. If you remember, we graphed out a force versus time, looked like that. The area inside was the impulse, but we also said that it may be more convenient to look at it in terms of the average force times time instead of looking at all this changing forces times time. So that's probably the more convenient way to look at it. One of the more popular things to do in class is to drop an egg and try to get it not to break. So what we're going to do is we're going to take an egg, drop it down, have it smack a hard surface. Now we all know what's going to happen. It's going to break. But then we'll do something else here. We've got a soft surface. And in that case, we don't really expect our egg to break. Once it reaches the bottom here, it's going to be okay. Whereas this is going to crack. Now, we want to look at the velocity right before impact. And we're going to call that our initial velocity. Let's call it negative 10 meters per second. It's moving downwards, decent speed to it. And you know what? If we drop it from this height here, we would have the same initial velocity over here, negative 10 meters per second in this problem over here. Now, afterwards, once it hits the ground, it's going to go splat. So the final velocity is going to be 0. Basically, this egg is going to lose all its momentum. You know what? The same exact thing happens here. And we'll give a mass of our egg 0.05 kilograms. Now, if you were looking at the change in momentum here, you're going to get the exact same thing in both cases because they have the same starting velocity right before impact and the same final velocity. All right, so it's no different. But what that also means is that they experience the exact same impulse, but one breaks and one doesn't. Now, I said most people don't like looking at the impulse momentum theorem written like that. They like it a lot better if it's written in expanded terms here. Average force times time for J, there's your impulse, and delta P we could write as final momentum minus initial momentum. And as I said before, these are terms that you guys should probably be more comfortable working with. And what we're going to do is distinguish between these two surfaces here. When you have a hard surface, basically it doesn't give at all. So the impact time is very short. And let's call the impact time here something very short. Let's say that T is approximately 0.01 seconds. Whereas the impact time here, since this is a soft object, what it does is it gives along the way. Now, it's still going to be very short, but we're going to call it 0.05 seconds. Point being here, this impact time here is longer than the impact time here. Not by much, though, right? A difference of 0.04 seconds. Now, based on that, we have all the numbers here to solve for the force that each of these things experiences. Let's do it for this one right here. If I'm looking at this formula here, the only thing I don't know is the average force. I do know the time is 0.01, and then we have 0.05 as our mass. The final velocity is 0 minus 0.05, and the initial velocity is negative 10. Note, you have to pay attention to sign here. It's very important. Working through the numbers here, and I'll let you do this on your own, but let me solve it really quickly. We have our average force times 0.01, that equals 0.05 times 0, minus 0.05 times negative 10. And let's see what we end up getting here. If I have not made a mistake, the average force I'm getting here is positive 50, and that would be in newtons. All right, now it's a positive number, which makes sense to me, because what that means is that this thing experiences an upward force from the floor. All right, that's what removes all the momentum, is that force right there. We'll do the same thing here. But if you look, we have a different impact time. So that number is going to change here. So our average force here is times the impact time of 0.05. The whole right side is still going to be the same thing, 0.05 times 0. There's our final velocity, minus 0.05 times negative 10. There's our initial velocity. And running through the numbers here, the only thing that changed was our impact time. So what I end up getting here is an average force of plus 10 newtons. Again, a positive number here. Now this force right here is smaller than this force right here. Basically, what we've done is we've kept the impulse the same. But if you were looking at the force over time, it's got a large peak here. What we're doing here is by spreading out that impact time, the area underneath may be the same, but we spread it out over a longer time, meaning the larger force that occurs here happens in a much shorter time, whereas you can get a smaller overall force spread out over a large amount of time. If you're looking at these two numbers, again, mathematical sign is very important. You get the direction of your forces from your answer. So basically, the impulse momentum theorem here is the guiding principle behind every safety device. If you can spread out the impact time, usually through something soft, like an airbag or some sort of cushioning, what that does is that allows you to undergo a full shift in momentum. You know, you're probably going to lose all your momentum in, let's say, an auto body crash. But if you end up spreading out the impact time just a little bit, a few hundredths of a second, let's say, you can really reduce the overall force that you would experience. Alright, I hope you enjoyed the first video. There will be more to come, but that's it for now.